So, this talk is going to be a little bit unconventional. So, as you can see from the plan, so I'm almost not going to have any results, and the only results I'll talk about are not my own, and some of them are not even correct. And and yes, and yeah. So I think yeah. So if you like this kind of talk, then you like it, and if not, then hopefully the other talks will make up for it. And so this is the plan, and I'm going to skip to the actual results about sum of squares in relation to problems in machine learning, unigames conjecture, and quantum information theory. Be happy to talk about them if people are interested during the breaks. Okay, so I'll start with a prologue talking about solving equations with radicals. So this was kind of all the rage for the first few thousand years of doing mathematics. And you know, the Babylonians came up with this solution for quadratic equations that we learn in, depending on the country, between, I guess, Indians probably learn it at birth, and Americans learn it in college, but and then for a long time this is all people knew, and it was actually like this was a huge part of doing mathematics and solving even particular examples, and in fact people would hold like these kind of duels where they would pose each other's equations, and then at some point in a story that has a lot of intrigue and some solemn oaths that were later broken, and then the solution for cubic equations and degree 4 equations was discovered and revealed and published. But then people still wanted to solve higher degree equations. There was this story of one woman who challenged these crazy 45-degree equations to all the mathematicians in the world, and teased the King Henry IV that none of these mathematicians can solve it. And then Vieta solved it. He realized this was something trigonometric. So even very, very smart people worked very hard on even particular cases. So Euler tried very hard to solve, to get a formula for degree 5 and couldn't, but solved some special cases. Lagrange, I think, tried to solve x to the 11 equals 1 and couldn't, but then van der Monde managed to solve it. And Gauss solved the equation x to the 70 equals 1 using only square roots. And this also amounts to constructing a 17-gon with a straight edge compass. And this was his first big result. He was very, very proud of this result. This is actually the result that made him decide to become a mathematician in the world. We still don't know how much the science of linguistics was set back, because that was his other option. And he wanted the 17-gon etched on his tombstone. But the Mason refused. He said he looked too much like a circle. No one would be able to know the difference. You can decide if the Mason or Gauss was right. So you know, everyone kind of, and you know, a lot of other people worked on these problems. Like Leibniz worked on it, and Descartes. And you know, so all these geniuses worked very hard on these kind of special cases, etc. But we didn't really understand what's going on until this sequence of work of Ruffini, Abel, and Galois, where they realized that some equations actually don't have a solution in radicals. And in particular, there is no general formula for solving degree 5 equations like there is for degree 2, 3, and 4. But they understood more than that. They completely characterized the equations that are solvable and equations that are not solvable using group theory. This is actually the birth of group theory and the notion of solvable groups. In particular, now we understand completely why you can solve x to the 17 with square roots, because 16 is because 17 is a prime of the form 2 to the 2 to the n plus 1, and we understand exactly why x to the 11 can solve it with square and fifth roots, because these are the factors of 10. And so we completely understand now these equations, etc. And as a consequence, we don't do this anymore. Mathematicians don't solve equations in radicals anymore. Now it's boring. And the thing that Gauss was so proud, this genius was so proud of, and wanted etched on his tombstone, is now something that you do with like few lines of Mathematica. And it's not because of the huge power of computers. It's just a very mechanical routine calculation now. So, okay, so this, what does it have anything to do with what we are doing? So now let's look at kind of what's happening right now in theoretical computer science, and a typical TCS paper, and actually not necessarily typical for this kind of workshop, but let's say people not doing log one. So in general, theoretical computer scientists, they come up with some interesting problem, some abstraction of some problem that people actually want to solve in reality. And then they do one of two things. Either they solve this algorithm, for example, Ford and Falkerson show that you can solve maximum flow or million other problems that are in P, or they show that it cannot be done under, right now under computational assumptions, as long as these, we are not able to get rid of these assumptions right now. The lower bound researchers, so prove that so sometimes you find an efficient algorithm, sometimes you find an hardest reduction, sometimes you show that in one parameter regime the problem is easy and in another is hard. And in both of these cases, these things require a lot of creativity. So every one of those problems is a paper on its own and requires a creativity to come up with the efficient algorithm or to show that it cannot be solved. So the question I'm asking is, can we make algorithms boring, like we did for solving equations with radicals? Yes?
My students think I've solved that problem.
Can we make it boring even for us? It's a challenge to make it boring for boring people, So this is a challenge, and this might be too much, but let's make it a little bit less. Can we reduce creativity in algorithm design? Can we make it somewhat more systematic? And this is not just to save work and to just save work, but because really what happened also in the case of equations, it's not just that you made things routine, you also understood them better. The reason that they're boring is also because you now understood them as a general principle and you have a much better understanding. So can we actually get a similar understanding, like we characterize the solvable equations, get the characterizations of the easy problems? The problems that can be solved in...
Different analogy could be with Hilbert's program, right? He wanted to, automate problem solving.
I'm trying to give an analogy with a successful program. Yes. Yes. So can we do that? So this is the question I'm asking, and let's try to understand this question a little bit, or the version of this question that I'm trying to ask better. So what does it mean to characterize easy problems? In some sense, characterizing the problems, the solvable problems, is kind of a universal solving routine. You want a single, simple algorithm that will solve all the problems that can be solved. That would be basically an understanding, a characterization of the easy problems. Exactly. So this is trivially true. There is a simple algorithm, very simple algorithm, that solves all the problems that can be solved. This is the algorithm that enumerates Turing machines. And what?
It only solves the problem. You can only really do that for NP intersectional NP problems.
I think NP you can do it if n to the log n time or whatever, put a clock on it. But in any case, this is also, I didn't exactly specify my goal. In some sense, my goal is also trivially false, because a simple algorithm should be an algorithm where we can analyze its running time. And if you could analyze the running time of a universal algorithm like that, you would settle P versus NP. In particular, we don't know, I mean, we have this algorithm, but I don't consider it simple because we can't analyze its running time. So in some sense, depending on how you phrase this goal, it's either trivially true or trivially false. So I try to find a way that it's neither one of those things. So let me revise the goal. I want a single simple algorithm that I can analyze. And I'm not going to prove that it's optimal. I'm going to conjecture that it's optimal. And probably not for all possible problems, because then again we'll go into trivialities, but rather in some interesting domain of problems. So this is somehow the revised goal. And the rest of this talk I'm going to talk a little bit about parts of this kind of research agenda. And in particular, the next slide, I'll say something about the interesting domain, but I don't have a good definition of the interesting domain more than some vague notions of what it might be like. The first part of the rest of the talk will be about what is this single simple algorithm that one candidate for this algorithm. And I don't have, partially because I also don't have a good sense of what is the domain, I also don't have any good, nice, clean conjectures. So I think even finding the right conjectures is still an open problem here, which I very much hope that some people will pick up. And the second thing is that once you have such understanding, even if it's only conjectured, you can get some byproducts. One of them is maybe new algorithms, which I'm skipping today mostly. But another thing is somehow, if you really characterize what efficient computation can do, you somehow can get better understanding of it, and you can get some kind of a theory of what computationally bounded observers know. And I'll talk a little bit about that. So this is basically the plan. Any question at this point? Okay. So here is the general domain. It's some undefined subset of combinatorial optimization. Now, I don't think everyone agrees what combinatorial optimization here, and I'm not attempting a definition. But here is some kind of properties that are commonly associated with optimization. So usually optimization, you're thinking of, you're trying to minimize or maximize some objective function subject to some constraints. And some examples that people normally include in this group are, satisfiability, max cut, max coloring, traveling salesperson, matching, etc. And some things that don't seem like combinatorial optimizations are like integer factoring, or like problems like Avi talked about for computing determinant, etc. And some properties of the optimization is that because we are trying to optimize some objective, then there is a natural notion of approximation that it's interesting to ask about, trying to get some of the objective. And there is also a natural notion of noise. Typically, it makes sense to talk about somehow perturbing the instance and asking for some robust kind of algorithms. There is relatively little algebraic structure in optimization. You see less of these magical cancellations that help you, say, compute the determinant or things like that. The world of optimization also seems a little bit cleaner in the sense that some complexity assertions that we don't think are true in general seem to hold like in this world, in the sense that, for example, in optimization, it's often the case that if a problem is in NP and in co-NP, then it's also in P. This is the notion of Edmonds called it good characterization. When a problem you have like you can certify that there is a solution, and you have a dual certificate that there is no solution. Usually there is also an algorithm. Also, quantum algorithms, D-wave notwithstanding, don't seem to do a lot. Don't seem to give exponential speed up in this domain. And often with these combinatorial problems, you also don't have these very strange algorithms like the number field sieve for integer factoring that run in time like 2 to the n to the 1/3. The problem are often either very easy or very hard. Yes?
Why do you think integer factoring isn't an example of combinatorial optimization? Every definition I would give for combinatorial optimization would include it.
Okay, so this is where we differ. I think of combinatorial optimization as satisfying these properties. and none of them holds for integer factoring. So if you want, you can think this is the kind of this is some unspecified class of problems that behave like this, and.
Algebraic structure, so you're not allowed to use multiplication.
Yes.
But are you allowed to use matrix multiplication?
That's also, I'm right now not distinguishing between, say, like, let's say, different polynomials, etc. So definitely, like, fast matrix multiplication, I kind of, it's too fine-grained to consider here. But yes?
Do you think the Hamiltonian circuit problem is part of combinatorial optimization?
That's a good question, which I was hoping to kind of sweep under the rug, even matching, etc. So okay. I'm not trying to define combinatorial optimization. In some sense, I would want to look at a subset of combinatorial optimization. But generally speaking, probably the kind of intuitions that I'm going to talk about are more appropriate for soft constraints than for hard constraints. So you can think of constraint satisfaction problems, or maybe some generalization of it, and possibly also Hamiltonian circuit. It's not something, or traveling salesperson, it's not something I thought enough about. But in some sense, I'm typically thinking of kind of soft constraints or problems that are robust to noise, where so if you wanted to solve, so you might want to talk more about longest path than exactly Hamiltonian, like trying to maximize the path rather than to say exactly it's Hamiltonian. But in one again characterization of this class that I'm not exactly defining is that the same ideas and themes keep recurring. So if you look at some great textbooks on optimization, you'll see some algorithmic themes that keep repeating again and again. Where for integer factoring, for example, or for other problems, you might have like very ad hoc ideas that are very, very specific to this problem. And one of those themes that keeps recurring is convexity, and this is what we'll talk. And the hope is that we somehow want to make this formal and say this theme for some class essentially characterizes what can be solved. So like I said, I'm going to talk about convexity. So I'm guessing that in this audience you kind of know what it is. So basically, if I wanted to minimize a function. If I wanted to minimize this function, it will be very easy. I will drop a marble and it will fall right to the global minimum. If I drop the marble here, it will probably get stuck in one of those local minimums. And generally this is why these kind of problems, minimizing a convex function is much easier than minimizing non-convex functions. So convexity is something that is used again and again and again. You see linear programming, semi-definite programming. You see general kind of convex programming again and again in algorithmic optimization. And the way it's usually used is the following. Sometimes the problem is convex, but often the problem is not convex. It's not even continuous. Most of the problems we talk about when we talk about optimization, at least we talk about, maybe some other optimizers actually talk about continuous problems, but we say minimizing some function over the Boolean cube, which is a discrete set. So typically the general TCS paper will look like you start with the interesting problem that you have. You find a way to embed it in some convex problem. You make a relaxation, and then you solve the convex problem. And for example, the set plus minus 1, the Boolean cube, we can embed it in the solid cube. And then there was this brilliant work of Gomez and Williamson that instead of embedding it in the Boolean cube, embedded it in the set of unit vectors and got something. Whose set of gram matrices is convex, and got some better results. And my problem with the work of Gomez and Williamson exactly is that it was brilliant. So the problem is that this step uses the C word, which is a dirty word in this talk. It uses creativity. So we want to get rid of creativity in algorithm design. Yes, yes, yes. We will going to force it to kill its own. Yes. So and this is where this kind of sum of squares algorithm comes in. So it's at least one method to try to get basically a universal embedding of any optimization, or like at least some optimization problems, it's in some technical sense it can be applied to any optimization, but it's really more natural to some of them and not for others, into an n to the d dimensional convex set. And this is kind of an algorithmic version, so it was done by different people independently, including Nahum Shor, Parillo, and Lasser. And this is kind of an algorithmic version of problems that arose from Hilbert's 17th problem of certifying that a polynomial is non-negative by expressing it as a sum of squares. And this is a kind of a universal embedding where you can make the convex set bigger and bigger by increasing this number d. As you make it bigger, it's less efficient. It runs in time n to the d. But it also becomes better in some sense, better quality. And typically in the problems that we care about, when d becomes n, then it's exponential time, but also solves the problem perfectly. And it turns out to encapsulate many natural algorithms, including linear programming, semi-definite programming, and a lot of combinatorial algorithms. And there is a very nice recent result of Prasad with Lee and Storer that showed that it's optimal among the natural class of semi-definite programs for solving constraint satisfaction problems. So this is the algorithm we are kind of going to look at as a candidate for somehow an optimal algorithm. And now, so this is the algorithm, the algorithmic candidate, and now I'm going to. So any question about this?
This last result that you mentioned seems to be along the lines of what you want.
Right, it's some kind of it's
More than that?
right. I mean, I hope that this last result is about some natural class that you can prove lower bounds for which unconditionally. Maybe we could hope that it's true for any polynomial time algorithm, and then we can't really prove this unconditionally, but we could still hope that it's true. Okay, so by now I've done, my dubious historical analogy. I philosophized about algorithms, and I waved my hands about convexity and the sum of squares algorithm. So I can now do the sudden shift to Bayesianism versus frequentism, and then talk about the non-results on the planted clique. So more things, good things are coming. Yes?
Yeah, you just relieve the topic. Does the sum of squares algorithm solve graph matching?
No.
Lower bounds for the SDP not solving it, but what about sum of squares in general?
I think I don't think it does.
There are lower
No, there are low bounds. Yes, I don't think it does. Yes. So again, there are these issues with kind of hard constraints that it does not seem super well suited for. Okay, so now what Bayesianism versus frequentist. So this is somehow one of the longest, I think, running feuds in science, which I've heard compared to the Shias versus the Sunnis, and it's less blood. Yes, only careers have been. So this is kind of a long-running feud between frequentists and Bayesians on these two camps of statisticians or probabilists. And one way to kind of to describe the difference between these two camps is to look at this statement. So as far as I know, people have computed pi to I don't know, the billionth digit, something like 10 to the 13, and they still haven't computed the 10 to the 20th digit of pi. So you could say, well, I mean, what's the probability that this 10 to the 7th digit of pi is 7? And so suppose you make this statement, the probability that the 10 to the 20th digit of pi is 7 is 10%. Then, frequentist, like Poisson, would say this is absolute nonsense. There is no we might have not computed it, but the 10 to the 20th digit of pi is either 7 or it's not 7. This probability is either 0 or 1. There is no sense in which this probability can be 10%. While, a Bayesian would say, so are you willing to take a bet with me? I will bet you, if you're willing to take 11 to 1 odds, I will bet you that, this digit is 7. So this is basically the difference. Bayesians kind of view probabilities as talking about beliefs, about knowledge. And while frequentists think of probability as being chosen from some sample space. And if there is no sample space, there is no probability. Yes?
You should take into your Bayesian account that someone is willing to make a bet that it is that one.
What?
So if you should condition on someone being willing to take the bet.
Yes. That might mean that they have computed it. Yes, that is that's one of the issues why I see a frequentist hiding here. That's one of the objections they usually raise about the subjectivity of probabilities. And yeah, so basically, I think as theoretical computer scientist, I was not even aware of this debate until not too long ago, because we are naturally frequentists. I mean, even when we pretend to be Bayesians, we use Bayes' rule. We do so with we really are talking about there is a sample space, and for us probability, is always some measure on a sample space. We think in worst case terms, which kind of corresponds to the frequentist thoughts, and so our natural tendency is to be a frequentist. But I want to actually go and talk about the Bayesian version of probability here, and it seems like. It might also seem like this whole debate is kind of like these kind of things like interpretations of quantum mechanics, where it doesn't really matter and all empirical predictions will be the same, but it actually is not the case, and definitely not the case where you take computational analogs. And so let's think of a more computational version. Pi was also a computational version, but this is maybe more precise. So suppose you're given this monstrous random graph. And I tell you, there is a clique here. The maximum clique has size k. And I ask you, what's the probability? What's the probability that vertex 17 is in the clique? So, information theoretically, this probability is either 0 or 1. This is it's completely determined what the clique is given the graph. And then the either vertex 17 is in the is in the set S, and if it's not. I just downloaded this graph from the internet, so I don't know the answer. But if you do know and find out, please let me know. Yes.
There's no vertex 17.
Oh no, it's this is the enumeration. But if you're a computationally bounded observer, you might say that my probability of this is more or less, k over n. As far as I know, vertex 17, especially since I didn't tell you which one is 17, is more or less the equivalent to all others. So, as far as I know, it's basically k over n, the probability that 17 is in this clique. So now I'm trying to make this kind of more precise. So this is kind of the Bayesian kind of worldview. And I'm trying to make this more precise. So we have this graph with maximum clique, and how does Bayesian think? So Bayesian will say we model our knowledge by defining this posterior distribution. So we have this distribution over sets, which we identify with 0, 1 to the n. And so it's a distribution, it sums to 1. It's a non-negative number summing to 1. And it needs to be consistent with our observations. So consistent with our observation, I would say, it's supposed to be distribution over cliques. So it better not have a positive expectation for a non-edge. If I and j are non-edge, then the expectation of xi, xj should be 0. So, and that kind of captures, that's a general Bayesian way to capture our knowledge. And the problem with this is that...
supposedly distribution on cliques.
What? Yes. Yes, this is supposedly a distribution on cliques. The problem with this is that, this is going to be... this really captures what the information theory. I mean, this has no computation in it, and this will really be only a distribution on cliques. So we kind of need to relax this to talk about computational versions. So I wanted to talk about computational Bayesian uncertainty, and it might not be clear how to relax it. And the way I'm going to propose to relax it is to change the word distribution to what I'll call a degree D pseudo-distribution. So what is a degree D pseudo-distribution? It's basically the same exact thing, except I relax one condition, and this is the kind of, this kind of strict insistence, this petty insistence on probabilities being non-negative. So the way I kind of view it, there is an Israeli saying that, it's okay to piss in the pool, but don't do it from the dive board. So the way I see it, it's okay to have negative probabilities, but don't be blatant about it. So, you can have negative probabilities, but don't be blatant about it in the sense that given that have that have a polynomial, a square low-degree polynomial that has negative expectation. So a pseudo-distribution is one that hides its negative probabilities and doesn't shout it from the rooftops, so instead of asking that for every x it's non-negative, we ask that the low-degree square polynomials will have non-negative expectation. Okay, so this is at least a well-defined notion. And note that the set of this kind of distributions, the set of vectors is a convex set. If I take a convex combination of mu and mu prime satisfying this condition, the convex combination also satisfies it. And it really is defined by only n to the d equations and some pseudo PSD constraints. So it really is. It might look like 2 to the n dimensional, but it really is in some n to the d dimensional, and you can solve it in time, optimize in time n to the d. And really, this is another way. This is the sum of squares algorithm. So the sum of squares algorithm for the clique problem, given a graph G, it will give you the maximum over all the degree d pseudo-distributions of the expectation of the size of the set. And a corollary of this definition, there are two things. First of all, if we look at degree n, so when we look at degree n, the delta function, the function that for every x just sets whether x is, just is one, the function for every x, the delta x function that on input y it outputs 1 if x equals y and 0 otherwise, is a degree n polynomial. And therefore, you can actually get this constraint. But when you go all the way to degree n, you actually get this constraint. So therefore, when you go all the way to degree n, then you get the clique number of the graph. The set of pseudo-distribution is the same of actual distribution. Generally, when you have lower degree, then the set of pseudo-distribution is bigger than the set of actual distributions because you have fewer conditions. And therefore, this number could be bigger. The sum of squares number is an upper bound on the clique number, which could be bigger. If you look at degree 2, then it turns out to be exactly the same as the Lovász theta function. So the sum of squares when you range d between 2 and n is somewhere between the theta function and the clique number.
So I don't understand how this max of expectation should correspond to a clique number.
So if you look at maximum of all distributions,
okay.
If you look at the maximum over all possible distributions on actual cliques of this thing, this would be the clique number.
Use over cliques, so you okay.
Yes. Right. Right, and when d becomes n, or 2n, let's ignore these issues, then this is the same as distributions. Pseudo-distributions and distributions are the same, because this condition implies this condition. When d is smaller, then you're maximizing over a richer set, and therefore this maximum could be bigger. And generally, this maximum will be, I'm not sure if I'm defining the theta function with respect to the graph or its complement, like, let's look at the theta function as when it is an upper bound on the clique number, and this number will be between the theta function and the clique number. Okay? So, and now, this is really defined with respect to the sum of squares, but as far as I know, there is no technical work that have done it, but in some sense, this notion of pseudo-distribution, I think, can be defined more generally. It might make more sense to with any proof system. So in some sense, you can think of, you have a sound but incomplete proof system. You might need some properties of this proof system, like relating in some sense to convexity, but I don't know what they are, and I've never written anything like this down, and I don't know if anyone else has. So, but this is somewhat of a general recipe. So you have like a sound but incomplete proof system, pi. And with sum of squares, you can think of it as a sound but incomplete proof system. Then a pseudo-distribution with respect to pi that is consistent with some set of observation has the property that if the observation tell you that a function needs to be larger than some number alpha, then the expectation needs to be larger than the alpha. So someone that is only restricted to drawing inferences using this incomplete system pi cannot detect that the pseudo-distribution is bad. And because pi is incomplete, this might be more general than an actual distribution. And in some sense, I think this notion of pseudo-distribution is the computational analog to Bayesian probabilities. And generally, the way I think about it is that, frequentist versus Bayesian is like if you take a computational analog to frequentist probabilities, you get the classical notion of pseudo-randomness. And if you take a computation analog to Bayesian probabilities, you get this notion of pseudo-distribution. And where the classical notion of pseudo-randomness with distinguishing, etc., it corresponds to algorithms, where here it kind of corresponds to proof systems. So it's...
What is an observation?
So it's a set of, so in our case, like it's supposed to be cliques, right? So you have some constraints that are supposedly, so it's supposed to be some pseudo-distribution over some set. And so this is somehow, I find it somewhat interesting that normally if you look at Bayesian probabilities and frequentist probabilities, they're actually like somehow technically the same. But if you try to make computational analogs, then it seems that you're led to very different notions, because this kind of corresponds to beliefs. But anyway. Okay, so now let me talk about the planted clique problem, because I do want to get a chance to annoy my friends. So this is a problem that I think originates, former friends maybe, originated with Dick, and the way I'm going to define it is not exactly the classical way. I'm saying you're trying to distinguish between a random graph and a random graph where we added the clique on top. And let's define it for this talk this way. And Lovash theta function gives for a random graph square root n value, and it's always an upper bound of the clique number, and therefore it solves this problem when the Lovash theta function solves this problem when the planted clique is larger than square root n. And there is no known polynomial time algorithm that does better than that. And this is really a very central problem in average case complexity. We don't have too many problems that we can serve, and that's been reduced to various things, and we really want to understand the complexity of it. And there is a theorem by Fagan-Krauthammer that says that the Lovash driver plus hierarchy, and you don't have to know what it is. It basically, in some algorithm that runs in time n to the d, it can detect a clique of size roughly square root n divided by 2 to the d. And this is basically the best trade-off we know. This is the best algorithm we know. And the question is, can the sum of squares algorithm, which is a generalization of this LS plus, can it do better? This is a question that lots of people were interested in, and therefore people were very excited when the two gentlemen sitting here announced that in fact sum of squares cannot do better, and cannot beat square root n for any constant degree.
So I think I was lost in the previous slide.
Yes.
What did you mean? Sorry, you said that SOS2G is square root of n.
So it means that the sum of squares with degree parameter 2 it's always an upper bound on the clique size. And in the random graph, it gives an upper bound of square root n. It means that if you try to plant a clique of bigger size, you will detect it, because you'll get different values in the random graph and in the planted case. So that's why the sum of squares algorithm can detect a clique when it's bigger than square root n. And Avi and Raghu claim that you cannot do better. And the way they proved it, they defined a pseudo-distribution. In fact, they looked at the same pseudo-distribution that was used by Fagan-Krauthammer. for this LS plus, and it's kind of the distribution, pseudo-distribution of maximal ignorance. Roughly speaking, basically, it's what I said before. They said, well, you know, look at every particular vertex, the probability that's in the clique, it's k over n. Look at a pair of vertices. If they are an edge, then, you know, if they're not an edge, then obviously they're not in the clique. But if they are an edge, the probability is roughly k squared over n squared with some constant, which I'm ignoring. And etc. And then they, you know, they reduced showing that this is a valid pseudo-distribution to a higher degree analog to common generalization of, you know, the Chernoff bound to matrix valued and also to higher degree polynomials. And each one of those individual generalization was known and true, and it seems like this definitely should be true. So, so they basically, it really seemed like this is all correct, but then, you know, some annoying guy came and showed that the concentration bound is actually false. But then, you know, you could still think, okay, maybe the concentrations, you know, they should have, you know, they have used not exactly the right concentration bound, and you can fix it. But then another annoying guy showed that, in fact, this pseudo-distribution is not a valid pseudo-distribution. Actually, John Kellner showed that there is a polynomial, quadratic polynomial, that it's, you know, if you use their pseudo-distribution, the expectation of p squared is negative.
And wasn't it the same in phi gay? Oh, that was just for LS plus?
So LS plus doesn't require this condition.
So it's okay for LS plus, but not for some.
Right, LS plus is okay for it to have this property, but for sum of squares, you cannot. Yeah. So. Yes, so and it turns out that things are not all bad. Like if you you are willing to go with a lower clique, then you know, and Raghu and Navi actually, and with Aaron here, and then later some other works that improve the exact number in the exponent show that this pseudo-distribution, this maximal ignorance pseudo-distribution, does work to show that sum of squares is at least not super great, but it still leaves open the question of this square root n. So now, I mean, I want to dwell more about like what exactly was the problem in Meka-Wigderson reasoning. Not because, you know, I'm just a person who likes to dwell on other people's errors. I mean, or at least not just because of this, but also because I think it actually can teach us something. So
Make more mistakes.
Yes. I think that some people's mistakes are actually interesting. So I want to claim that, you know, they didn't make just a technical error; they made a moral error. And the moral error is that, you know, you should, violating, you know, Einstein's maxim. Einstein said, or he didn't exactly say that, maybe, that, you know, pseudo-distributions should be as simple as possible, but not simpler. And another way to say it is that pseudo-distributions should have the maximum entropy, but they still need to respect the data. They need to respect the observations. And this maximal ignorance pseudo-distribution has lots of entropy, too much entropy, doesn't respect the observations. And the reason it violates Bayesian reasoning. So let's think about it. Okay, so think of the, you know, the expectation. You look at some vertex I, like we said, and you want to know what's the probability that I is in the clique. And initially we said, well, the probability is k over n, but let's think a little bit more. If we're true Bayesians, let's think a little bit about what data we have and how we should interpret it. So one thing we definitely know about this vertex is its degree. And generally, it's a random graph. The degree is going to be n over 2, but not exactly, right? It's going to be n over 2 plus minus square root n. And you might think, okay, no, my plus minus square root n is not a big deal. It shouldn't really change a lot the probability. But let's think about it. So basically, this is what Meka-Wigderson said. They said it's essentially k over n, maybe 1 times like little or up to lower order terms. So the maximal ignorance distribution said basically this probability is k over n. But let's think about it. So if let's be Bayesian. So if I was not in the clique, then its its degree is just a random, Poisson variable. You can think of it as a Gaussian with n over 2 expectation and n over 2 variance, so square root n essentially standard deviation. But if it was in the clique, then it's shifted. You have k more neighbors. So it's basically, roughly speaking, it's like n over 2 plus k expectation and the same standard deviation. So these two random variables are shifted, but notice that if k is almost square root n, then this shift is almost a standard deviation. So this is actually some significant difference in these distributions. And therefore, when you see that a vertex had degree n over 2 plus square root n, you should give it higher probability than, like some significantly higher probability, say 1.001 factor more than if you see a vertex that had degree n over 2 minus square root n. And so more technically, you should really reweigh the expectation of xi by the probability under this versus the probability under this, which, it's proportional, it's a reweighing, so constant factors don't matter. It's proportional to something like this, where if you think of k as roughly square root n and delta as roughly square root n, this is basically like 1 plus some small constant. Plus or minus small constant, depending on whether delta is negative or positive. And in fact, if you do these Bayesian moments, then, in this new work that there are some people here that are co-authors on, you actually do get square root n for degree equals, for degree 4, and it's still wide open on whether you get above that. So now, let me end. Why did I find this so interesting? So the reason I find this error so interesting because it really shows that sum of squares captured Bayesian reasoning where LS plus couldn't. And in some sense also like this notion of Bayesian reasoning, at least to me I find this very interesting because in some sense a way to try to attempt to define what a computationally bounded observer knows. And maybe it could be useful in some other setting, maybe even in computational economics or other settings where you could try to basically have a theory of like what is knowledge for computationally bounded observers. And it's also somewhat, it turns out that this is kind of a way to design both lower bounds and algorithms, and some of our works kind of try to use this pseudo-distribution to design algorithms. Now, a lot of people might say, there is absolutely no reason to assume that, sum of squares is the optimal algorithm. And I agree. And this is still in its infancy. And one of the reasons I'm trying to make these bold claims is because I hope that people will, give bold counter examples and help, try to give people motivations to refute them. But I think that unless we see a very good reason that this quest is completely hopeless, we really should not kind of give up on this kind of dream of trying to find for some class of problems, especially these kind of combinatorial problems where it seems that ad hoc tricks are less needed and there are more common algorithmic themes, to try to find some kind of a more general theory that tells us what is hard and what is easy and how to capture knowledge. It's somehow too attractive a dream to kind of give up. So even if sum of squares is not the answer, I hope something else is.
Questions?
Yes.
This analogy with solving equations is supposed to tell us the time scale. So in 2000.
Yes, that's a good question. Where are we in this request? Are we like the Babylonians, or are we like the Italians with their duels, etc.? It's
Okay.
Yes. One comment. As much as I wish we use as exponential moments, I don't think those are quite the moments we use.
I know this is the moments you will use. You don't know it yet, but in the final version of your paper, this is the moments you will use. Yes. Yes. Yes, when I gave this talk at Cornell, some said, "Well, thank you for not, for being relatively mild with the things you promised that I will prove." So he was afraid I will, commit him to proving even much more things. So.